Hello guys, welcome to Hot Coder. In this video, we are going to see the Leetcode problem number 212 word search tool. So let's get into the question. So the given problem statement is we'll be given a m into n board of characters, which is m into n matrix, which will be containing of characters, and also you'll be given a list of strings words. So you need to return all the words on the board. So each word must be constructed from letters of the board sequentially adjacent cells of letters of sequentially adjacent cells where adjacent cells are horizontally or vertically neighboring. So the same letter cannot be used more than once in a word. So this is the problem statement, and that so let's get into the approach. Let's take the test case one. So yeah. So before solving any question, we need to define the problem clearly. So we define the problem. So the input for this problem will be a board of size m into n. It's a two-dimensional array. It will contain characters, and output of the solution should be list of words. So they will also give the first input is a board, and second input is a list of strings. We have as a string array words. So we have two inputs, which are a matrix which contain characters and words, string array words which contain many words. So finally we need to return the list of strings. So finally we need to return the list of string. So list of words which are present in the board. So list of words which are present in the board. So how can we solve this? Before solving, we need to check know about the problem clearly. So what are the characters that are present in the board? So the characters are lowercase, so as mentioned in the question. See, sorry, each character in the board is a lowercase letter. Yeah, so lowercase. The characters in the board are lowercase, and also the character in the words are lowercase, as they have mentioned here. And what are the other conditions? So are the words in the given words are unique. There may be duplicates, right? So uh, in the problem we have mentioned that the words are unique. So this is another condition. So words are unique, lowercase and unique. So that's it. So and also we need to see the minimum length of the word. So what will be the minimum length of the word? So in the question they have mentioned that word's length will be at least a size 1. So minimum length is 1, and the the board also contains at least one element. So they have started given that it will be having a lower bound of 1. So that's it, and we have defined the problem clearly. So now let's get into the second step for solving a problem, which is to find the approach. So approach. How are we going to approach this problem? So we have copied it. So we copy the test case. So what would be the first thing to do? So this is the board, and let's see the words. So these are the words. There are four words, I guess. Yeah, these are the words, and we need to check the presence of given words in this board. So this is the board, right? This is the board, and this is the word. We need to check whether these words are present in the board or not. If it is present, we'll add it to the answer. So yeah, uh, we'll add the words to the answer and return the answer. So this is the problem here. So how to approach this? So initially we start with every cell and move the, and they are also given the important problem definition, which is direction in which we can use words sequentially. Direction. So from each cell we can move up or down or left or right. So from each cell we can move to this direction. So which we this is a case which I have missed from the problem definition. So yeah. So how can you approach this problem? So we can start with any index. So every index. So we'll start with every index and every cell and move on to and form the word. So form the word and check whether the word is present or not and continue. So initially we'll start with O. So we start with so we will give indexes to rows and column. So initially we'll start with O and we'll move down. So we add it to E. I mean the string builder. So let's call it as a string builder. So we'll go to I and upon the I and into I and upon I we cannot move down. So we'll move right F. So L, and we'll for each time up, while we open we'll check whether the current word is present in the words or not. So we will append each character and check. So we'll check append and check, append and check. So each time we'll append the character and check. So this will return us the result, but the time it takes will be order of, let's say, m equal to n. So in worst case, let's say it is maximum possible. So n into n, since we start from every cell and we move on to every cell, maybe the max worst case will be moving to every cell. So this is the condition, and this is the this will lead us to u of n power 4. So this is the, we start with every cell and we move to maximum word length. So word length. So let's have word length as m. So the time complexity will be go of m square into m. So this will be the time complexity. Can we improvise the approach? And the answer is yes. And how can we improvise? So from each cell. So yeah, I have created. So copy it again. Yeah. So while we start from each cell, we need to move. We are trying for every direction. So instead of trying for every direction, we are just going to try in valid directions alone. So consider we are starting with O. We have possibilities to move to E or A, but we are going to move only to A. Why? Because when we consider each word, a word which is starting with O, um, there is only one word which is starting with O. So from that word we can only move to A. So we can move to A. We'll avoid this move. So we'll avoid moving to E. So by this way we can optimize this approach. So consider we have two words like oath and so E and A. Consider this is the fifth word of the words array. So when you start with the cell, so let's consider this cell. We have possibilities to move left or up or down, right? So will you move to every direction? The answer is no, since the words that start with E are only yeah, the second letter are E, A and N. So we can move to A and we can move to N, and we'll avoid this path. So in this way we can eliminate this paths, so it will be more efficient. And can we start with K? So the answer is no, because there is no words in the word array which is starting with K, so we can avoid this. So by this way we can optimize this approach. So which data structure will be useful in this case? So can we use so from each word to check whether it is valid word to start with, how can we find it? So and also from each word, how to check the next valid words and which to avoid. So in this case, try data structure will be solving the issue here. So try data structure is a data structure which will be forming like a tree. So there should be a dedicated video for try data structure. In this video we cannot include the try because it will take a lot of time to explain about the try. It is a just simple, but it may take up to some time. So I'll discuss about the try data structure in other video. So I'll give you the basic intro about what try is. So try is a data structure which will be looking like a tree. So consider the this try as a class. So try will be consisting of, let's say, current value. So it will be having a value and children. So it can have, let's call it as a node. So try node as node. So node can have a value and child of the current node. So we call it as, it can be a list or array, right? So let's have array. So array of nodes, let's call it as, so let's call it children. So each node is nothing but part of the data structure. So let's call it this as node. So this is a node, empty node, and this empty node can have a value. So let's say we have O. So we are building a node, try node O, and we have children, right? So let's call, let's see for word both. How can we form the structure of both in the data structure? I mean try data structure. So we'll have a word O. Initially we'll have root. So initially we have a root which will be empty. Let's have it as empty, and it can have many children, right? So it can have any children, any number of children. So before that we need to know where we can use try. So where we can use try and why. So we can try the data structure which can be used to search, insert, delete, for delete words which has some prefix, based on prefix words or any other data. So let's say I even have a number or any other nodes. So in this case we will consider words. So delete words based on prefix. This is the main point to be noted, prefix. So we can also use slightly modify the try to make it compatible for suffix. So the suffix is just reversing the word. So prefix can be also replaced by suffix in the try. So this is why we are using the try. So it can be used in the places where we have this functionality as required. So that's all about the try. So let's see the insertion of each word. So initially we'll have try as empty. So initially we have one node which is the root of the try. So let's call it as root. And the any node, any try node can have any other. Uh, it can have any number of children. So in this case we have chosen array, choose array. So while creating we'll be declaring the array. So when we have list, we can add any number of child. So initially we have root. So let's insert the word both. So how will we inserting? So O, from root we have O, then A, then T, followed by H. So we'll insert the next word, which is P. So from root we don't have P, so we are creating P, and we'll move to next letter. So we don't have E after this, so we are inserting E, and we don't have A after E, so we are inserting A. Yeah, we have completed the second word. We'll move to third word, which is eat. So from root we don't have E, so we are creating a E node with a value of E, then A and T. And how can we insert rain? So rain can be inserted by using R, A, I and N. So let's consider we are inserting a word ENA. So how can we insert? So from root we'll check whether the node E child with node E is available or not. Yeah, it is present. So we'll move on to this direction. So let's have another brush. So we'll move to E and we'll check whether N is available or not. So firstly we have taken the first index, we'll move to second index N, and N is not available, only A is present. So we'll create a node for N. And we'll move to next word, next character, and add the A. So we have inserted, successfully inserted all these words. That is 1, 2, 3, 4, 5 words. So 5 words, we have inserted 5 words. So we'll firstly build this try. So firstly we'll create a try and insert all the words. So this is going to be our first step. And second step is going to be, we are going to start with every cell and moving on to only valid directions. So valid paths. So when we consider starting with O, so when we start with O, we can only so initially we get root, and we'll check whether we can start with O or not. So yeah, root has child O, so we start with O. So we just have other marker. So initially we start with O. Yeah, O is a valid case, so we can start with O, and we'll move to A. Move to A. So whether we'll check whether we are able to move to A or not. Yeah, we can move to A. So we'll move to A, and from A we'll check. We have two possibilities: either to move to A or D. We cannot move back to O since it forms a cycle. So in the question they have mentioned that and the same letter cell may not be used more than once in a word. So when we form word, we can only use the word once. So we cannot move backwards. We'll check for right whether we can move to A from current A. So we can see that from current A there is no nodes with A available. There is only T. This is T. So we can only move to T. So we'll ignore this path and we'll move to T. So from T, we'll check where to move on. So from T, we can move. So in this cells, we have three possibilities: either to move to E, R, A, or T, H. So these are the three possibilities. Let's have another color. So let's have purple. So we have possibilities, three possibilities. So we'll check whether we are able to move to A or not. A from T, there is no A available, so we'll ignore this path, and we can check whether there is a path to E or not. E is not available, so we'll ignore this path, and we'll check whether H is path to H is available. Yeah, the path to H is available, so we'll move to H. So finally, we can clearly see that we have reached the end of the word. So I have reached the end of the word. So we'll add the word to answer. So we have formed a word which is available in the word. Since we have reached the end, so we'll just add it to the answer. It's called answer as it have answer. So we'll add the word current word. So OATH. OATH. Yeah, we added the word oath, and we'll check with every cell. We'll start with every cell and follow the same step. So initially we'll start with the root, and we'll keep on moving down. So we are going to use a DFS. So we'll use DFS and move on. So finally we can also see that there's a word eat. So there is a word eat. So we start with E, A and D. So this is also a word available in the board. So we have successfully added to the answer, and finally we'll return the answer list. So in the question they have mentioned the answer should be in list. So we'll return the list. Yeah. So we're going to revisit our approach. So the approach, the approach we are going to use is firstly insert every words to try. Every words in words array. Every word. So every words in words array to try. So next we are going to create answer. So we'll start with every cell of the board, and finally we move to every possible way. If we reach the end of a word, if reach the end, we'll add the current word to the answer. So this is what the fourth step of our approach. So you'll be very clear in the coding session. If you are still unclear about how to implement all these steps, we'll get a clear idea in the coding session. So let's get into the coding section. Yeah. So initially we'll have a data structure as try node to store the node values. So in this case, we don't need to have the character value. So yeah. But we'll have it for their clear understanding. So character value and array of nodes children, and also will do boolean value. So we have a string variable word. So We'll have a constructor for try node, which will create new array of 26 characters. So we are using 26, only using 26 space sized array, because in the question they mentioned that every character will be lowercase. So we can represent the word lowercase a to z by using 0 to 26, 25 indexes. So that's it. So initially, first step is insert every node to every word. So okay. So we'll create a root in try root. So we'll create a try node which will act as a try root. So yeah, the consider we can pass a data which is val. So we'll store it in the current node value. So we'll create a new try node as a root. So this will be acting as a root node. So we'll insert every word. So we'll use a enhanced for loop. So we'll use a helper function, add words of root comma, which will pass this, and yeah. So this is the first step, and the second step is going to be searching, starting from every index, right? Before that we'll create a array. So we'll create a set answer. So we'll have a set of string answer. We just in the set, yeah, we have created the set. And next step is going to be start with every cell. So we're going to start with every cell, and we're going to call a helper function, add words, and we'll pass board and I and j, and yeah, we have passed this. So what are the additional parameters which will be required? So we also got the answer set and also root. So we'll pass this, and finally we convert the set into list. So they are asking us the list value. So we can return the list. So answer list will be new array list of answer set, and return the answer list. So that's it. We write the helper functions. So first is add words. So we'll use a DFS to add the words, or even you can use a iterative approach. So we'll use DFS in this case. So private void add words. So firstly we'll get the root and list words array. So we're going to add the words in this function. So for each word we are going to iterate, use the iterative approach here. Since DFS approach will be a little more unclear. So it is a very easy approach, but we need to explain it very deeply. So I'll be using a iterative approach here. So for each words, we are going to have a list. I mean, try node yes root. So we'll have an index I as 0 while I is less than word dot length. So we're going to move to every index of the current word. So initially we'll get the children of the current node. So P will act as the current node. So node array children will be P's children. So if it contains, so usually get the current character, which is word dot character I, and we'll see whether current there is a node child node of the character ch. So we'll reduce by 97 to locate the uh, child, I mean the index of the current character, which is ch. So if the node is the child of current node is empty, which will be in case when it is null. In this case, children of ch mentioned will be new child node of ch. Yeah. So after this, we'll update the current row to I mean current node to children of 97. So after this, we'll increment the I. So when I meets the end of the word, the loop will be breaking out, and we'll mark the word as end. So we'll store the word here. So p dot word will be current word. So yeah, we have successfully written the input function to add words, and so this add words to, let's have this as input function as add words to try. Since both the function are having same name, we'll just change it. Yeah, so add words. This will be the core function. So in add words, we'll get the parameters which are character board and current index, current row and current column, and set of string answer and root, which is try node, current node. So yeah, we have all these values. So we can have this board as a global variable, since using more parameter will be slightly confusing. So we'll have a global array, and when we enter into the function, we'll store the global variable. Yeah, so we'll store it, and yeah, so if current root is end of the word, so when it is end of the word, the roots, the nodes word will be not equal to null, right? So yeah, so in the try, the final node, so when you take a try, so consider this as a try. A, so initially this will be hash x e. Consider this as a try, and in the current last final word, the word value will be x. In other words, the word will be null, right? So we'll use this word data to find whether the word is, I mean the current node is the end of the word or not. So in this case, this is the condition we are using here. So if root is the current root node is end of the word, we'll add the word to answer and return, or else firstly we'll get the children. So children of the current node, which will be root dot children. So if we'll get the current character, which will be character ch, will be board of I, right? So we'll take the current character. If there is a child node with current character, if it is null, we'll just return, or else what will we do? So if there is a node that is children, we'll use the base condition below. So in this case, we'll check whether the child is end of the word or not. If the child node is end of a word, we'll just add to the answer and we'll return. Or else we'll move to every direction. So we have a base condition like if I is less than 0, j is less than 0, or I is equal to board dot length, or j equal to board dot length, board of column n, or board of current word is already visited. So we'll use the dash to indicate current word is visited. So in this cases we'll return. So yeah, we have taken the word, and if the child of the current node representing the current character ch is empty, will return, or else we check whether the child is the end of the word or not. If so, we'll add to the answer, or else we'll move to all directions, right? So we'll use add words of. So we'll firstly mark the current word as visited, cell as visited. So we'll move to the all four directions, up, right, down, and left. So I plus 1 j answer and children of cs minus 1, and next action is let's have our next action as up. So I current row minus 1 and j, and we'll have j and also the answer. So I minus 1 answer and children of cs minus 1. We'll move left, and j minus 1 will take us to the left index minus 27, add words of I comma j and right of ps minus 27. So yeah, finally we'll update the current shell as not visited. So we firstly have marked as visited, and next we'll use the replace the same character, that is original character. So that's it, and yeah, we have written the function. So let's check the sample test case. So um, what happened if a bad operand tries for binary operator? So this will be double equal to, and there's an error in the third line. So it is a array of try nodes, right? And 55, 59. So all are the same error. So we'll check again. So cannot find, yeah. So we are going to add the children's word. So we can replace the root as children of this management. So we'll update change the root, since we don't use the root in any of the below lines. We'll just replace the root by the child node. So we'll just use root in all these cases, all these lines. We'll run it. So root.root. So yeah, it's accepted, and let's check for next test case. Accepted. So let's submit it up. So on the answer. So what happened? So we are given the board, the words OA. So we are not adding the second word. So what mistake have we done? So we'll check. Firstly, we'll form the matrix, the paint. So this is the board, and so these are the board. So what are the words? So these are the words. So initially, let's say for OA will be starting from O. I'm going to write A, and this word is present, so we'll mark it as OA. So we don't need to return here. So let's because yeah, I'll say whether why I have taken return this because let's take this. So when we are trying to find the word OAA, what often happens here is, so I erase this up and we check for second word OAA. While we so yeah, we'll start with um, here. When you start with OAA, so we'll have marked O, we'll move to A, and we have met A, and in the try, initially we have a try rate, which will be O, A, this is the end of the word, so OA, word, and also OA, which will be having end as OAA. In this case, when we move to A, when we start from here, first we have reached A, and we'll move to A. T is not there, only A is present, so we move to A, and we have reached the end of the word. So in this case, initially we have written end here, that is will return here. When we use not return, we have eliminated, deleted the return statement. We'll again move to next word, next node. So we'll move down and we check whether the word is empty or not. It is not empty, so we'll add this to the set, and finally we'll be able to add both the words. So OAA will be the answer. So let's check it out. We'll use the same test case. Yeah, it will work fine. So check it out. Yeah, it's working fine. So let's submit it up. Accepted, and the time complexity of approaches order of m into n. Let's say n into m n square into maximum word length. So let's n square equal to, so this is the worst case, and the space complexity of the approaches, all the possible words. So the possible words will be like 3 into, so all the possible words, so order of word max length into 26. So yeah, the worst case space complexity and approach for this problem is using try. Yeah, we have used try. So and also hashing. So that's all about this problem, guys. Thanks for watching this video. Have a great time.